the organizers for both inviting me and also for organizing this lovely conference. I'm very excited to hear all the talks.
Actually, I have one correction. So the timetable says your lecture is from 10 to 10:50, but it's supposed to continue until 11 because you have 50 minutes.
Make up 10 minutes of it. And yeah, I'll be talking about surfaces and p-adic fields. And this is works that I did during my PhD under the Minyoung team and the Konstantin article.
Are you right? And I ask, usually the lecturer is filmed, but this time, this looks like the audience is being filmed.
Yeah.
What is it?
So that's for Zoom talks when there's a remote audience and when you ask a question that the camera will come to you, broadcast it to us.
Well, we don't have any remote participants. The camera is swinging, so
Yeah, check this out.
I can also see the reactions later.
You're not being spied upon. But we have a very sensitive microphone up there that's picking it up and controlling the camera.
So I guess the main idea started from Minyoung asking, well, the problem that Minyoung kind of gave me for my PhD was it could be quite nice if you could say something about the outer automorphism absolute Galois group of QP or a p-adic field, and whether you can say something about how it acts on representations. And I guess this comes from kind of a few things. So the first intuition that I was given was this arithmetic topology dictionary of Mazur and Morishita, Kapranov, and Reznikov. And I'll just briefly mention this analogy, but there's definitely people here who can tell you much more about this analogy than I can. So yeah, just kind of quickly say that under this analogy, if I have a spec of a number field, of a number ring, then this should correspond to some 3 manifold or S3 vaguely. And if I have primes, they should correspond to knots. And I guess what I was more kind of interested in was this the local case. So as I said, so kind of under the classical dictionary, so p-adic integers should correspond to some tubular, so some knot K, and this should correspond to some tubular neighborhood of the knot. And then when you look at the p-adic field, then you would get the boundary of this tubular neighborhood, so some tubular neighborhood of K, and this should be the boundary of it, which gives you some torus. Kind of one of the main reasons for this is when you look at the tame part of the Tal fundamental group of spec of a P, say, or something like that. Then what you would get is that this is equal to a thing generated by 2 elements with the following relation, tame ramification relation. And then up to this extra twist, it looks like a torus. My kind of main thing that I kind of felt is missing in this analogy, well, it doesn't really account for the whole fundamental group, and it doesn't kind of account for highest genus and what happens if I take some extension of QP and I guess kind of the other thing is, well, under this analogy, what should I expect out of the QP to look like? So this theorem of Mochizuki tells us that if I have two p-adic fields, some finite extensions of QP, then we have the following bijection. Between the isomorphisms of the fields and the outer automorphisms between the two Galois groups, the absolute Galois groups. But here we have this extra condition on the ramification filtration having to be preserved. But I was kind of interested in asking what happens if we take away the ramification filtration. And following this kind of analogy, well, if QP should be thought of as some surface, so yeah, here it should be. Then, well, what is outer automorphisms of pi1 of a surface? This is the mapping class group. Of the surface, which I will say a few words. So what is the mapping class group? Well, one way to think about it is just outer automorphisms of pi1 of S, but usually it's kind of a much more geometric definition, which is that this is equal to the homeomorphisms of S mod this identity component, which I will not really define. And one of the nice things about the mapping class group is that this is generated by Bain twists around simple closed curves on S. So yeah, I wanted to have a nice analogy of Dane twists, which will act very similarly to the Dane twists in the surface setting. And so using tools which were already kind of existence, but mainly for discrete groups, they were used in a group theory. One can define what is a Dane twist for kind of a general group, but then there's still work to kind of check that these Dane twists are non-trivial in the outer automorphisms, and that they actually potentially generate, but at least have some of the nice properties that the Dane twists in the classical setting have. So yeah, kind of the main purpose of my work was to try and kind of not only strengthen this knowledge, but kind of have a uniform way to look at both the surface setting and the p-adic setting and terms for them. So I'll kind of quickly. So So to have a uniform setting, I used the Mushkin groups, which I will explain in a second. So these are graduality groups, maybe ropey graduality groups. Of dimension 2. So what do I mean by that? These are G, some propy group. With the following properties. So I want H1 G with coefficients in FP to have a dimension, some finite dimensional H1. I want H2 to have dimension 1. It's group cohomology. And I want to have non-degenerate bilinear pairing from H1 to H2. And
Via couplet.
Huh?
Via the couplet.
Yeah,
You want it to be non-degenerate.
I want it to be a non-degenerate bilinear pairing. Yeah. Okay, and kind of examples for this is exactly what I wanted. It is Rho-P completion of I1 of S and maximal Rho-P quotient of the absolute Galois group of a p-adic field. And I'm writing it here. So it's a type of maybe route, just assume. And that's the pth roots of unity are inside of K. And when the pth roots of unity are not inside of K, then this maximal Rho-P quotient is a free group, which can correspond to a surface with punctures, but this is kind of slightly harder to work with the outer automorphisms of the free group. This is so as kind of the first step, I'm working with the mapping class group of a surface. So they both have fairly similar structure. And what would be the structure? So theorem, so such a the Mushkin group has if I have a Demushkin group, then there exists as its orientation character from G into the p-adic units. This will be associated to kind of a graduality group in general, and in particular of dimension 2, and to given of the Mushkin group, I have this orientation character, which would kind of be the cyclotomic character for the case of a p-adic field. And it would be trivial for the case of a Rho-P completion of a surface. But so suppose this orientation character
What is UP
p-adic units.
in K or
No, just ZP.
ZP?
Yeah,
B star.
yeah. So yeah, just
Easy to see why the orientation character exists.
yeah, I don't think it's too hard to prove that. So you have this dualizing module, which you can prove exists, which is which represents yeah, and this just as this orientation character is isomorphic as an abelian group to QP mod ZP, and G acts on it, and via the action of G on this dualizing module, you get this map because the automorphisms of this dualizing module is exactly ZP star. So yeah, suppose this orientation character vanishes mod. So vanishes, I mean, is trivial. Mod p to the r, but not mod p to the r plus 1. And suppose that G is generated by by D, which must always be even. This is again some easy fact to prove that for the Mushkin group it must be well, I don't know if easy, but yeah, it's a fact that the Mushkin group must be generated by an even amount of generators. So I have this Demushkin group, which has an orientation character which vanishes with p to the r, but not mod p to the r plus 1. So G as a pro P group is generated by two P generators. And the following relation, x1 to the p to the r times the commutators times the product of the commutators. Just note for K being an extension of QP of degree n, then V is equal to n over 2 plus 1. We're here, and this R would be the maximal power of P, such that the P to the R roots of unity are contained in K, but P to the R plus 1 is not contained in K. So knowing just kind of what is the degree over QP and what roots, P roots of unity will be inside the field, we have this nice presentation of the maximal pro P quotient. And note that if I take this kind of extra twist away, this is exactly a surface of genus D.
Is the statement that there exists such an R?
As there exists such an I for any Poincare duality group.
No, R. Yeah.
Oh, R? Again, yeah, there exists such an R. This is basically from the fact that, yeah, you just take this linear pairing for the trivial P, not trivially mod P. Yeah, so for existing, because here you take FP with the trivial G action on it, you have this pairing. Okay, so we have this Demushkin groups, and then the question is, what would be a Dane twist? And so I guess the first question is, what would be a simple closed curve? And so in general, for a group G,
So this result is already due to Demushkin? Or?
it's due to Demushkin for p not equal to 2, and then for p equal to 2, you have some similar result due to some other people. But yeah, this result is Demushkin. So yeah, for a group G, at least for me, a simple closed curve is graph of groups with cyclic edge groups. I explain all of these in the talk. Cyclic edge groups and fundamental group isomorphic to G. I would also call this a splitting. So yes, this is kind of some combinatorial way to think of all of this. And what do I mean by graph groups? I'll talk about kind of the simplest types of graph of groups. But yeah, so suppose we have this surface, and I have a simple closed curve on it. So kind of you have this S and by one of S, and by Van Kampen theorem we have this nice thing that pi1 of S1 amalgamated product over pi1 of alpha, pi1 of S2. So this is now isomorphic to pi1 of S. And similarly for every curve that when you cut along it, you get two connected components, you would get such splitting of the fundamental group. And if you take something here, which is non-splitting, so you get only kind of one connected component. So in this case, you have another notion of something called an agent and extension, which tells you how to reglue everything. It's S prime, so this would be I1 S prime I1 beta. This is beta. And if I have multiple non-intersecting curves, then I can just kind of iterate this process to write a fundamental group of a surface as fundamental groups of simpler or smaller surfaces, of lower G surfaces. And So what do I mean by a graph of groups? Well, for every component that I would get in here, I can instead write a vertex and joins them by an edge for the curves that I cut along. And so here I would put I1 of alpha. Here I would put I1 of S tag. Here I would put I1 of S tag. And well, a fundamental group of a graph of groups, one way to kind of think of what it is suppose I have a more complicated graph, and I have A, B, C, and alpha, beta, and gamma. So I take one edge at a time and I collapse the edge. And instead of each edge joining two vertices, I will write on the new vertex that I collapse an amalgamated product. So this is equivalent to writing B amalgamated over gamma C, A, alpha, and beta. And here I'll collapse it again, and I would get alpha B amalgamated gamma C amalgamated beta A.
Could you switch the black box like the top one? Oh, you can't move the top one. Okay.
Yeah, I would if I, yeah.
No, you could write, I guess you can, maybe you don't need this or.
Yeah, I guess I'll just rewrite it here quickly.
So the example at the corner corresponds to a loop, or
Yes, so I was just about to explain what a loop is.
The second example is not a simple closed curve.
It is a simple closed curve. It's just not, it doesn't split it into, doesn't separate it, sorry. So there's a separating and a non-separating. Separating would be one giving you two components, and non-separating would give you as one component after you cut along it. So yeah. So eventually, after you collapse these edges, you get this B amalgamated over gamma C amalgamated over beta A. And here you still have alpha, so I want to now collapse it. And like I said, if you have something which is non-separating, or if you have a loop, basically, then this corresponds to this thing called H&N extension. And so we get that the fundamental group of this would be the following. So all of this is amalgamated over alpha. And why do I require that all the edge groups? Well, I could take edge groups to be not isomorphic to Z, but if I want it to correspond to curves, then I do want it to be isomorphic to Z, because it needs to be a fundamental group of a curve. But this kind of game, this notion of graph of groups can work also when I split over, say, surfaces, because up to now I've mainly worked with surfaces, but if I want to work with three manifolds and I cut along some subsurface or something like that, then you can also have a notion of this. And so I'll quickly explain then what a Daintwist is. So given any kind of a graph of groups, I can define a Daintwist associated to this graph of groups. And so suppose I have the following situation of A and B amalgamated over this cyclic subgroup generated by C. So this would B as generators and relations just be the thing generated by A and B with their generators and relations. And this extra condition that basically phi C is equal to, well, C embeds has this phi A, which is a map from C into A, and phi B, which is a map to C to B, and I want this phi of A C to be equal to phi of B C. And then I'll call this splitting alpha, and so the Dane twist associated to alpha will be the thing that sends A to be equal to A for every A in A, and for every thing in B, it will be conjugation by the generator of the thing I'm amalgamating over. And for an A and N extension, so suppose I have A, C, and I have two maps into A, I1, I2, both are maps from C into A. So the A and N extension would be the thing generated by A and this extra generator T. And the relation would be that the inverse. Yeah, so T phi 1 C, T inverse is equal to phi 2 of C. So we have this relation. And then in this case, the Dane twist would be, again, act trivially on A, but on T, send it to C times T. And one can check fairly quickly that this is exactly what usual Dane twists do on the fundamental group of a surface. So now the question is, well, given a Demushkin group, what would be all of the splittings over ZP now, because we're working with pro-P groups. And then once we know what all the splittings are, will these two automorphisms actually be non-trivial on the outer automorphisms? And what would happen to their powers and what would be the relations and all of these questions. So kind of the main approach that I took, and I see as my work as kind of a first step towards lots of other theorems that I believe can be proved, is look at the classical proofs in geometry of how you prove that, say, the Dane twists are non-trivial in the mapping class group, and then try and rewrite everything in the language of groups. And then there's also this kind of extra step now of checking that when you move from the discrete world to the pro-P world, you don't lose stuff, because you might have that it will be not inner discretely, but then it suddenly becomes inner in the pro-P world. So luckily, these are kind of all the things that I managed to show. So first of all, in the case of surfaces, you only need one discrete group to kind of get all the information in the pro-P world. Whereas for general Demushkin groups, so suppose I have G some Demushkin group. And with invariant P to the R. Then we have a family. Discrete groups R prime, where R prime is greater or equal to R. And I'll write them down in a few moments. Such that all ZP splittings of the G from nice Z splittings of R prime. So this means not only do we have many splittings over ZP of our group, but also I can write down explicitly what they are. I'll come back to this in a few moments. And then the next one is that the splittings coming from the discrete Dane, the outer automorphisms coming from the discrete Dane twists inject into the outer automorphisms of G. So we don't lose any information when we go to the pro-P world. And also for every alpha, so for every splitting of G over ZP, and for every K integer, P alpha to the power of K is not trivial in the outer automorphisms. So
what is script GR prime?
uh,
The discrete group
yeah, it's the discrete groups, which I'll write down explicitly in a moment.
from the Galois group. You make a discrete group.
I make a lot of, like, there's a family of discrete groups all completing to my Galois group with the maximal pro-P quotient. But yeah, I need to look at more than one discrete group in order to get back all the splittings of the pro-P group. Because yeah,
Does it finally generate?
each one of these, yeah, finally presented.
Thank you.
And actually, so this one kind of like final corollaries I managed to show recently is that maybe not all of them, but this family. So yeah, like I said, these are finally presented and have infinitely many. Some of them might be isomorphic. I don't know how to show they're all non-isomorphic, but they do have infinitely many isomorphism classes. And for every L, including the prime P, but for every prime, the pro L completion of all the JR prime are isomorphic. So this is kind of interest more to group theorists, where they ask, given discrete groups, can you tell if they're isomorphic or not from their pro-P completions, from their pro-finite completions? And this is kind of a negative answer, a nice kind of negative example. And their pro-L completions for every L not equal to P will be a free group, and for L equal to P will be a Demushkin group. So what are these GRs primes? So first of all, these GR primes would be the group generated again by 2D generators. And the following relation, it's almost the same one. But we add this extra twist on the other side as well of some power greater or equal to R. And checking kind of the cohomological properties, one can show that they have kind of the same cohomological properties as the Demushkin group with just a twist on the left. And then due to this classification theorem of Demushkin, they must be isomorphic. And just going to note that when R prime is equal to infinity, then we just take ID. So we just So what do I mean by this? I just mean we get the kind of regular Demushkin group relation for R prime equal to infinity. And this kind of also explains why you only need one discrete group for as a surface setting, because there you're already at R infinity and you're only taking R primes greater or equal to R. And what do I mean by this subscript T? And what do I mean by this nice splittings? Well, I take, so the Dane, or yeah, so the amalgamated ones would be splittings that under kind of some base of generators can be written as F to the 2n over C. So this is the free group on 2n generators and the free groups on D minus 2n generators. And this would kind of correspond in the usual setting to just separating the surface into a genus N and a genus D minus N components. Yeah, D over 2 minus N, but yeah. And then C will map in here to X1 to the P to the R. X1, Y1, Xn, Dn. And here it will map into Y, P, P, so R tag, YD, XD. Y n plus 1, xn plus 1. So why do I get this kind of extra splittings? Well, in a sense, what happens is this would be like two relative Demushkin groups with orientation character vanishing mod R prime and vanishing mod R. And so the orientation character of when you join them will vanish just mod, well, the lowest one will be R. Which is why this kind of doesn't contribute, because all you care about is the maximal quotient in which it vanishes. And then for H and N extensions, it's enough just to look for R prime equals infinity. So for the splittings over H and N extensions, it's enough just to look at R equal infinity. But in general, okay, maybe give the general thing. So these are things for which the map will, so this would be on D minus 1. Equal to FD minus 1 amalgamated over C, where the map into it would be yd to the minus p to the r prime, x1 p to the r, and then x1, y1. And under automorphisms of this discrete groups, this will kind of give me everything. And this is similar to how in the geometric setting, you can always do a change of coordinates to get your splitting either to be just, so all the HNN extensions, you can always move them to just be curve around here. You kind of always do a change of coordinates, and for a splitting, you can always change it into something where all the information that matters is into how many, in what are the geni of the components that I cut into, which is kind of what I'm saying here. All I care about is this n. And yes, so this kind of theorem, all of them having nice, is exactly saying that up to an automorphism of my Demushkin group, any splitting will have either this kind of very nice form of being a curve, just so that you can write it on the outside, or just cutting the surface into lower genus components. And then the way to prove this theorem about Dane twists, I guess the main component into that is, so like I said, I can always move my components to be on one of the sides. So suppose I'm given a splitting, I move it to this standard form, and now I want to show that it acts non-trivially. So how do I do that? I looked at, so there's a notion of intersection of splittings, which corresponds to intersections of curves on a surface. And this nice thing about intersection of splittings is that, well, first of all, an intersection of a splitting with itself is trivial. Every curve doesn't intersect, every simple closed curve doesn't intersect itself. And that intersection of conjugation is equal to, if I conjugate one of the components, then this doesn't change the intersection number. And so what I do is, if I have this alpha and this beta, I show that the intersection of T of alpha of beta with beta, well, I take curve alpha and I take another splitting such that they have non-zero intersection. And then I show that when I do the Dane twist on the splitting beta, the intersection is again non-trivial. And so it cannot be just conjugation. And same with powers. And this kind of theorem of moving from the discrete world to the pro-p world is kind of a bunch of playing around with taking the correct pro-p quotients to show that I can have conjugacy separability conditions, and that the groups are residually p, and that splittings kind of complete nicely, and this kind of things. So yeah, that's the vague sketch. Yeah, I think that's my time.